Hello and welcome to Lecture 5 of Chemistry for the Interdisciplinary Sciences. Today we're going to have a look at some covalently bonded molecules like the ones behind me. So let's just jump straight into the learning outcomes. By the end of this video I'd like us to be able to define the term covalent bond, to write a molecular formula for any drawn molecule, including some skeletal structures that we'll have a look later on. We're going to recall that the non-metal elements hang out as diatoms on their own when they're in the elemental form, and identify from the periodic table how many bonds each element is likely to make. So that's something that the periodic table tells you as well. Finally, we're going to identify and name some simple alkanes, and I'll go on to talk about why that's useful, why it's useful to know the names of some of the compounds, and what we do with covalent compounds on the whole. So last lecture we were looking at compounds containing metals and non-metals, so elements that want to lose electrons partnering with elements that want to gain electrons, and that being a favourable thing to happen. Today what we're looking at is compounds containing only non-metals, so compounds where both elements want to gain electrons. And you can imagine that already is a difficult situation, isn't it? If everyone needs just a little bit more resource, then where does it come from? In general, covalently bonded molecules are discrete whole units. So by that I mean things like, see the molecules behind me, there's separate ones, they're all little triangle shapes, but there's lots and lots of separate molecules. The same is going to be true for the molecules that we look at today as well. They tend to be small, we call them simple molecules or simple covalent molecules. They tend not to have a charge once they're bonded completely, though later on in the course we will see some examples of some charged covalent compounds. But on the whole, they're insulators, they don't conduct electricity. And some quintessential examples is water, CH4 is methane, that's what comes out of a gas hob, and CO2, carbon dioxide, that's what also comes out of a gas hob once the flame has happened. So, let's have a look at some covalent bonds in the first place. Both of these hydrogen atoms have one electron in their outer shell from the periodic table. We'll just pop that up. So up there in the top left is hydrogen. Each one has one electron. It wants one more electron because there are only two elements on that row. So that fills up its shell. And so the only thing that hydrogen atoms can really do is come together and share their electrons in pairs. So a covalent bond is where the atoms are sharing a pair of electrons. And we draw that covalent bond like this. The two separate elemental symbols there, H and H, and then the stick in between them representing those shared electrons. If we have a look at each of these circles representing the hydrogens, we'll see that both circles contain two electrons, even though each electron technically belonged to one atom at a time. Now you might be wondering why pairs of electrons? Well, the answer is because what's really happening is the orbitals of the atoms are coming together. So the atom has electrons hanging around in that one repeatable cycle. When these two atoms come together, we create a brand new repeating cyclic path that encompasses both of those nuclei. And again, now we're thinking about the concept of that wave travelling around two separate nuclei, instead of just that, the sun and the planet. Now we've got two planets and we've got to have our orbit happening there. So that creates what we call a molecular orbital. You don't need to know that term, but we had atomic orbitals, now we have a molecular orbital, and still any orbital can only hold two electrons. It's exactly the same reason as before. The negative charge eventually causes repulsion, and the two electrons in one orbital are attracted by basically being north poles and south poles in a magnetic environment. You don't need to know that either, it's just interesting. So an orbital can hold a pair of electrons. In this case, we now have our hydrogen nuclei hanging out there, and they are positively charged, remember, because they're nuclei. And those positively charged nuclei are being held inside a sort of gigantic cloud of negative charge. So those are our positive nuclei, trying to draw them on the outside. And in this case, because each hydrogen provided one electron, we've got two electrons hanging out. So now we've got two positive charges and then an area of negative charge in between that physically holds the atoms together. And so if I pop back to that illustration I had behind me before, now what we've got is physically an oxygen atom here in the red being attached to these two hydrogen atoms, and it will float about like that, all three of them together, bound together in physical space. So let's have a look at some other elements. What will they do when they bond? Because unlike hydrogen only wanted one electron, didn't it, there, to complete its outer shell. Do all the elements want just one? No. So how can we tell from the periodic table how many bonds an atom needs to make in order to complete its shell, which again, I'll remind you, is what all atoms are trying to do. They're trying to get to that full shell electronic configuration. Carbon on the periodic table is in group 4. It's in the 2p2 position. It's got a proton number of 6 there. That's C for carbon. It has 4 electrons in its outer shell in total because it's in group 4, and therefore it needs another 4 electrons to complete its shell. That being the case, it needs to form 4 bonds because every bond offers 1 electron from each atom into the other atom's orbit, if you want, or into the other atom's shell. Nitrogen is in group 5, so it being in group 5, there it is in the 2p3 position, proton number 7. If it's group 5, it has 5 electrons in its outer shell. It needs 3 more electrons to complete its shell, and so nitrogen will form 3 bonds. Oxygen is in group 6, and so it needs to form 2 bonds. It needs 2 more. Hydrogen we already saw was in group 1, but in the top shell, in the first shell we only have 2 electrons there to fill up the orbitals. And the halogens, so that is all of group 7, fluorine, chlorine, bromine, iodine, all in the p5 position there. They all need 1 more electron to complete their outer shell, and so they will only form 1 bond at a time each. So let's have a quick look at this water molecule I've got here. Now, this is water, it's H2O. So if we look at this structure, we've got 1 oxygen atom and 2 hydrogens, and that's what makes it a H2, lowercase there, denoting that there are that many 2 of the element before them, hydrogen. Hence we got H2O here. Now, if you had been told that that was the formula and you tried to draw it, you either would have drawn that structure or you would have drawn this one. So H, H, and then O. And so let's figure out which one is correct and why. Well, oxygen, it says in this row of the periodic table, of the table above, needs only 2 electrons. So that means that oxygen has to always form 2 bonds. In the top structure, oxygen it's got those 2 bonds there. In the bottom structure, oxygen is not happy at all, so we're going to put a big cross between that. The hydrogens each should have 1 electron or 1 bond to complete its electrons, and yet we can see each hydrogen here has only 1, whereas this hydrogen in the middle there has 2, so that is also incorrect. You can imagine that once you understand that and you start trying to put the atoms together, there are only a few possible structures for most formulae. So what's happening electronically? Over here we've got oxygen in the middle, and again we'll have a quick glance at the periodic table. Yeah, oxygen has 6 electrons in its outer shell because it's in group 6. It does have a total of 8, but don't forget the first 2 are in the shell above, in the first shell, and then there are 6 in the next one. So that being the case, I'll just quickly number them. I've represented those with the purple line, and actually perhaps I should be using a purple pen here to make it a little bit more obvious. So that's electron 1, electron 2, electron 3, and I'm just doing this in case you can't see the purple colours. 5 and 6. So those are oxygen's 6 valence electrons. What do I mean by valence electrons, by the way? I mean outermost electrons. So the 2 electrons in the shell below for oxygen, the 1s2 electrons, aren't available for bonding because they're right in the middle of the nucleus, or rather very close to the nucleus, and so not available for swapping electrons with anything else. The other thing is, it's a stable shell. It doesn't want to bond. That's a definition of a full shell. Each hydrogen atom here is offering 1 electron over. So that being the case, then we can see that if we look at the hydrogen circle in total, so this whole circle, it's got 2 electrons in, so it's happy. This hydrogen circle also has 2 electrons in, 1 green and 1 purple, or a numbered 1 and 1 in a box if you want. And if we look at all of oxygen's circle there, we can see that it also has 8. 6 of its own, and 2 from hydrogen. And so every atom here has completed its octet, which is fantastic. That suggests that covalent bonding leads these atoms to a more stable configuration than before, because we end up with full shells, just to clarify that. So that's why atoms would ever form covalent bonds, because it helps them get to full outer shells, full electronic configurations, without having to give up electrons. They can just share them instead. Let's have a look at some other then hydrides of the other elements on that row. We got hydrogen and chlorine. Actually, chlorine's the one below, but fluorine would be the same. So there we've got the halogen. The chlorine there is in group 7. It only needs one more bond, so hydrogen is single bonded to chlorine, and that's the end of it. Oxygen here. Now notice that oxygen does have the same structure as we drew before, but we've got these two little pairs of dots. They represent the electrons in the last one that were not involved in bonding. We call these lone pair electrons, so because they're not being shared in any way, they just belong to that one atom. They belong on that atom itself. So there's oxygen with its 2 bonds, hydrogen again only having 1 bond, brilliant. Nitrogen here has its 3 bonds, and notice again it also has a lone pair of electrons that aren't involved in bonding, but still nitrogen with 3 bonds, great. Now carbon has 4 electrons, and it needs 4 electrons, so they pair off together to give us no non-bonding electrons there. And so again, carbon has its 4 bonds to the hydrogen. So hopefully those structures make sense to you. Let's just think about now writing the chemical formulae. So here for H and Cl, it's just HCl, isn't it? We've already had H2O for water, so that one's fine. Here we've got 1 nitrogen atom and 3 hydrogens. So I'm going to write that as NH3. And here we've got a carbon and 4 hydrogens, CH4. Now, water is a bit weird that the hydrogen comes first. Usually the way it works is you do carbon, hydrogen, and then all the other elements. So don't be too worried about the order of the elements just now. Just be aware that that's how it's done. Now, it's not always the case that atoms are just bonded to hydrogen. They can, of course, be bonded to other non-metals like oxygen, nitrogen, and so on. So here we've got a string of 4 carbons together. But notice that each carbon atom here has that sort of compass point configuration where it's got 4 bonds. So every carbon has 4 bonds, every hydrogen has 1 bond. And all that's basically happened is we're repeating that process over and over again. So this is one way to represent the structure of it. And again, let's think about the chemical formula. So I want you to pause now and give it a go. What's the chemical formula of this compound? Okay, hopefully you've paused. So we have C4, because we've got 4 carbons in total. And then we got H10, because there are 4 there, and then 2 there is 6, and another 4 is 10. So we'd say C4H10. Now, I think you can see that this is a really blooming long way to write the structure of this compound. It takes ages and ages to write CHH and so on. As chemists, what we tend to be doing is using lots of different lengths of these molecules, lots of different lengths of carbon chains. And so what we do, first of all, is we can talk to each other about them using a naming system. So here's the naming system for our alkanes. An alkane, by the way, is a molecule containing only carbon and hydrogen where it only has single bonds. So with most molecules, the way it works is you start off with a prefix which talks about how long the carbon chain is. So if it's just 1 carbon, it's meth, and then eth, and then prop, and then bute. So that's those first 4. And then after that, you might notice on this table here, it's basically the names of the shapes with that many sides. So pentagon, hexagon, heptagon, octagon, and so on there. You don't have to remember after that, you'll already know those. But up to that, meth, eth, prop, bute, you will need to learn, because I will be talking about those lengths of chains quite a lot in this course. So it might be worth you coming up with a mnemonic that means something to you. 4 words that start with M, E, P, and B that will stick in your head to remind you that it's methyl, ethyl, propyl, butyl in there. So that's the start of it. The start of the name says how long the carbon chain is, and then the end of the name, in this case the ane, is telling us and what is the structure like. In this case, it's like an alkane, which is just carbons and hydrogens single bonded. There are lots and lots of different functional groups, we call them, which just basically means common bonding structures. So maybe there's double bonds in there, or there's oxygens, or there's nitrogen atoms. And those all have different names. So for instance, if we're talking about alcohols, we might have methanol, ethanol, propanol, butanol. But in this case, we've got methane, ethane, propane, butane. So let's quickly write the molecular formulae for these compounds. So propane, well, we have C3. And then I'm noticing that each carbon has 2 hydrogens attached to it. And then there's also a hydrogen at each end, isn't there? So there's almost a general formula that we could make here, but let's just prove it. So we got C3, H, well, we got 6 there, and 2 on the ends is 8. Here we've got C4, and then we've got H, well, 2 4s are 8, plus 2 is 10. And down here we've got C7. Now look, it's such a pain for me to count up those hydrogens. So all I'm going to do instead is say, well, there's 2 for every carbon, so that's 14. Plus 2 is 16. And that takes us to a general formula for our alkanes, which is CnH2n plus 2. I.e., however many carbons you have twice as many hydrogens plus 2 for the hydrogens on the end. You don't necessarily need to learn that. It's just a bit of a shortcut for you, so don't worry if you don't think you can learn that. You'll always be able to count it out of the structure itself anyway. Now you can see that heptane is already a pain in the bum to draw. Look how long it is, and then I've got to draw on all the hydrogens for every single one. In chemistry, we're quite lazy, and so we have a different way of writing structures, which is called the skeletal structure. The way it works is, instead of having to write carbon every time, what we'll do is just draw the bonds in between them, and we'll just assume that if the atom isn't written in between them, so it's not obviously an oxygen, like that for instance, if there's nothing there, then we'll assume that's a carbon. Now notice also in this structure, so these two things, to my mind, to my brain, are exactly the same thing. I'm representing the same molecule. It's just here, I haven't had to write in all the carbons, and also I don't have to write in the hydrogens. Because in a skeletal structure, what you assume is that any bonds that are not drawn are hydrogens. So in this case, if that was a carbon there, how many hydrogens would it need? Well, it only has 1 bond drawn, so you must need 3 more bonds in total. And so that takes us back to the same structure there. Let's just prove that that works for all the others. So, yeah, there's 2 there because this carbon atom has 2 bonds already. This carbon atom, that needs 2 more bonds as well. So that's that. And then this carbon atom at the end, that needs 3 bonds in total. And so we've got that. So notice that the skeletal structure there, I managed to convert it straight back into the structure that I had before. And so again, this skeletal structure, which is just showing the backbone of the carbons, is exactly the same as the other structures and will be much quicker for you to learn to write. So there is going to be a workshop on this later on, but this is exactly equal to the other ones. And if I just tell ChemDraw that they're carbons, look, it fills out the rest of the structure for us. It knows that there'll be 3 hydrogens there, 2 there, 2 there, 2 there, because what was already drawn tells us how many are left, how many are left over. Now let's very quickly have a look at what those molecules physically look like in real space, because so far we've represented them in a sort of 2D way that is really flat here. So what do these molecules actually look like? Here we have all the atoms we need. So what I'm going to do is make an ethane molecule, or actually shall we make a propane? Yeah, let's make a propane, that might be more fun. Oh, I'm a sad man. So what I'm going to do is put together these atoms and physically look at what the 3D shape might look like. So first I'm going to put together all my carbons. Now, how do I know which atom is a carbon and which is a hydrogen? By the way, this is my cat, don't worry. Well, this is a carbon atom because it has 4 holes, and the holes aren't very easy to see. So can you see in the hydrogen atom there that there is obviously 1 hole, and all the rest of the sphere is complete. These black ones here are the same, it's hard to see the holes. So this carbon has 4 holes, and that's how I identify it as a carbon, because if we went back to the slide over here, we say, oh, it's got 4 valence shell electrons, and therefore it must form 4 bonds. So that's what we've got going on there. So let's put the carbons together. So again, this would lead us to our sort of skeletal structure. Now, notice there, I've got those 3 carbons, and they're in this sort of weird triangle position. If I just pop back to ChemDraw for a second, if I were drawing this skeletally, well, it would be that, wouldn't it? So you can see that shape there, that sort of upwards roof shape, is exactly representing the 3D structure of this compound. So there we go, we got that. Now I've got all these spaces left for our hydrogens, and basically all I'm doing is filling in the holes with these bonds. Oh, I did not get enough bonds apparently. Now, the hydrogens are being represented by these little white balls here, and they're little because their shells, the electrons in those shells, are only in the 1s orbital, aren't they? And here, with these carbons, we're talking about the 2p section. So I put all this together like this. Yep. Aha, that's where that bond went. So last one. Ooh. Let's take that off and put that one on. Ta-da! So that is propane there. We've got propane because there's 3 carbons. You can see its physical structure is sort of bent. And what it will be doing in the real world is all of these would be rotating all the time relative to each other. So this molecule would basically just be always rotating about. It wouldn't fall apart like that. That would actually cost us a lot of energy to do. So that's a propane molecule. Again, we can figure out its molecular formula. It's C3H1, 2, 3, 4, 5, 6, 7, 8. C3H8. Still filling that CnH2n plus 2 rule as earlier on. Now, why do we care about this is a reasonable question. In chemistry, one of the things that we do is create medicines. So here we've got a medicine, tamoxifen. It's actually an anti-cancer compound in there. But it is following the same the same conventions as my physical model here. So the black atoms are carbon atoms, and the white atoms are our hydrogen atoms. Now let's have a quick look at the other ones. So here we've got a red atom. How many bonds does it have? It's got 2 bonds. So if we went back to that table, it would suggest that that's an oxygen atom. And up here, this blue one, it's hard to see, but it's got 3, so it must be a nitrogen atom. So can you see that the skeletal structure that's drawn over there on the right-hand side represents quite well the actual physical structure of the drug that's modelled over here. Now let's just make sure that it makes sense to us. So what this is saying is, in between the oxygen and the nitrogen, there are 2 carbons, aren't there? This is a sort of ethyl linker. And we see that there as well. 1, 2. But can you see how the skeletal structure is relatively easy to look at without having to show us the rest of the hydrogens and all the rest of the structure? The nitrogen has 2 methyl groups attached to it. So when I say methyl, I mean 1 carbon long, if you want. And those methyl groups, look, they're there. So there are those methyl groups. Over here, look, we've got an ethyl chain, so a 2 carbon chain. Where is that on this structure? There it is. There's the ethyl chain. So you can see that the drawing can represent quite well what the structure is. Why do we care? Well, the way that this molecule functions is basically by having those ring structures. You see the ring at the top here that's sort of out of the way, and at the bottom here. What it will do is force those rings into the DNA of a cell and cause that cell to die. And that is what we want when we're treating cancer. We want those cells to die in that process. So in chemistry, a lot of the time what we're thinking about is putting together chains and links of a certain shape, because this molecule will have the perfect shape to get into that DNA and change it in some way. And that's the same for all the uses of chemistry. We're trying to find molecules that are just the right shape to do what they need to do in the body. So that takes us back to those alkanes then. It's really important that we learn the names of those lengths of the chains. We're going to mention them quite a lot as we go forwards. Now, let's have a quick think about the elements themselves. So if I didn't have black and white balls, I only had one colour, what would they look like? So the elements have to just the same. If they were hanging around all on their own, just nitrogen atoms, they're going to have to share electrons and form covalent bonds, because it's still going to be two non-metals trying to bond, isn't it? So they're going to have to share electrons. I want you to think about the chlorine atoms. So the chlorine atoms, how are they going to bond together, and what will that look like? So I want you to give it a go. Try drawing it and see what that looks like. Well, I saw out my green screen a bit. There we go. Okay, so pause if you need some more time. But essentially what's going to happen is each chlorine atom wants to make one bond, so it's going to look like that. The first chlorine is going to be attached to the second chlorine, and then they're both happy. How about the next? Oh no, yes, let's look at this. Which is the correct molecular formula? So I want you to have a think about that. Pause this and think about which one is the correct molecular formula, the most correct. Okay. So let's go through it. A here, Cl, is clearly wrong, because that only is one chlorine atom, and we very obviously have two chlorine atoms up there. 2Cl, now a big 2 in front of a number means that there are two of this whole unit that comes after it. So if I had two separate water molecules, I would write a big 2 and then H2O to say I've got two separate ones. So there I'm thinking about having two of these at the same time. So 2Cl is not correct, because that suggests two separate chlorine atoms just floating around all on their own, not attached to each other. So that one is also incorrect. Cl2, yep, that works perfectly. The lowercase letter there, number, sorry, telling us that there are two chlorine atoms. That works, that one's fine. ClCl, yeah, that also is a molecular formula. It's okay. I'm going to give that a M. It's okay. It's not too bad. And we do specifically use this for, like, if I said something like CH3OH, I'm saying the H twice there because the fact that it's an OH is important. And again, we'll talk about that later on. Finally, E, is that one correct? No, it's not, because that is showing the structure. And that's the difference. This is a molecular formula. It's telling you what atoms are there in this compound. The structural formula tells you how they're connected. So here, I don't need any covalent bonds, thank you, in any molecular formulae. You're just going to write how many atoms there are themselves. Okay, so what about nitrogen then? So if elemental nitrogen has to form 3 bonds each, I want you to suggest a possible structure. So again, pause it and have a go. Okay. So, a really common thing to do at this point would be to say, okay, I've got a nitrogen atom, so there's my first one. It's bonded to another nitrogen atom. That nitrogen atom needs to have 3 bonds, so it's bonded to 2 nitrogen atoms. That nitrogen atom needs to have 2 bonds, so it's got that, and so on. And you can see that that would end up in what we call a giant lattice. Now, carbon does do that. Carbon needs to form 4 bonds. It forms 4 bonds with other carbons, which form 4 bonds, and that makes a diamond. We're going to talk about that later on in lecture 8. But for now, we need to think about, well, this is probably not the easiest solution then. I'm going to have to get all my nitrogens in a row, and they're all going to have to bond together. And I know that nitrogen is a gas, because I'm currently sat at the bottom of a sea of it. So that suggests that nitrogen probably is a smaller molecule than that. And what actually happens is, once you've got the first 2 nitrogens together, you can imagine it's much easier for those nitrogens to bond again with each other than to wait for another nitrogen to come along and bond to it. And so what's actually going to happen is, nitrogen is going to form 3 bonds together. And so that would be drawn like that. 3 separate bonds. Each bond represents a pair of electrons here. So we've got 2 electrons there. Then that's another 2 electrons. And then that last one is another 2 electrons. That being the case, these nitrogen atoms are being held together by 6 electrons on the inside. And then remember, each nitrogen atom is going to have a lone pair of electrons. Because it has 5, it uses 3 in bonding. I tried to do this earlier and it didn't work out. So we got those 3 is all it needs to do. And so we've got our 2 leftover lone pair electrons there. So that's what nitrogen looks like. And in fact, all the elemental gases do the same thing. So oxygen needs to form 2 bonds. It makes its first bond, and then it'll make its second bond as well. Oxygen will have 2 lone pairs left over. Now, I don't expect you to always write the lone pairs or anything. I'm just showing you that where they are because it's helpful to think about at this point. And then we already saw chlorine doing the same. Hydrogen will do the same too. So carbon is the only one that doesn't. And that is because if we had 2 carbon atoms coming together, it'd have to form a quadruple bond. And that's too many electrons in between the atoms themselves. So that many electrons in that physical space would just repel each other. There is also a problem of the orbitals not being in the correct direction. I'll talk about that in an optional lecture that I've also included this week, but it's completely optional. You don't have to do it. This is properly first year degree level chemistry, but it helps think about it. So if you're going into a chemical progression, biochemistry, something like that, it might be worth having a quick look at hybridization at this point, just to make sure it makes sense. Or if you're just generally curious and you're in physics and you want to know, then do watch that one as well. So there we go. Generally, any elemental gases of the non-metals are going to occur as diatomic molecules. By diatomic, I mean 2 atoms together. And so we go back to the last screen. NNOO, Cl2, and so on. So there you go. If you're asked in a question, hydrogen reacts with iron, for instance, then you would write H2 plus Fe. Before we had iron elementally is just Fe. For the non-metals, they're going to hang around as in pairs, and so we're going to see those as H2. Okay. So enough prattling. So why do we care about this? Well, here are some compounds that are, human-made and nature-made. So we've got aspirin. Aspirin is human-made in that a compound called salicylic acid comes from the bark of a willow tree. We basically just add this group over here to that compound to make aspirin. What does aspirin do? It goes into the bloodstream and promotes water being delivered into the blood to basically provide water to areas that are hurting. So if you've got a headache, quite often it's that your brain has dehydrated and it's pulling on the tissue inside your head. So by providing that water back in the bloodstream, aspirin tends to relieve pain that way. It's a really good blood thinner. So that's us humans putting together molecules, and you can see that they're not very complex. You look at neomycin, which is an antibiotic. It kills certain types of bacteria. You can see it's much, much more complex. But still, it's following the exact same rules in the skeletal version as it is before when we expanded it out. So let's have a quick look at then aspirin's actual physical structure and see what it looks like. So here I've got the structure of aspirin. What I'm going to do is put it in the same orientation as we have it on the slide up there. So that's like that. There we go. Perfect. So that is exactly what we have in the skeletal structure shape up there. So let's just look at what we've got. We've got these carbons in a ring, or we could start here with the oxygen. So this red one is an oxygen because it's only got 2 holes on it. Oxygen is bonded to the hydrogen, and that has a carbon there. That carbon is double bonded to an oxygen, and then it goes down to this sort of hexagon shape here, where we have alternating single and double bonds. So where it's purple, there's 2 bonds, and then we've got 1 there. They alternate, goes up to this oxygen that's sort of a bridge in between these 2 carbons. There's carbon with double bond O, and we've got this carbon at the end here. Now let's just look at the things that have come out from the skeletal. Can you see, first of all, it's basically the same shape as we have up there. So that's helpful. It lets us keep track of what the physical shape of the molecules is. But also notice at the end here, I've got that carbon. If you look in the skeletal structure, it's only got 1 bond, and it doesn't say that there are 3 hydrogens, but by filling up the holes with hydrogen when something isn't written, I've made myself a little CH3. That's a methyl group again over here. Here on the rings, there's no hydrogens written, but if you have a look at them, there's only 3 bonds for these ones. If you're looking in this position, 2 from the double and 1 there, leaves 1 bond left over to bond to hydrogen. And so that's what it would look like if we expanded this structure out to show all the atoms. But look at this nice little flat structure here. Again, this structure is perfect, both in terms of shape, but also in terms of the nature of the electrons. Notice that these oxygen atoms here in red, don't forget they each have lone pair electrons on them. So they're quite electron rich, each of these little red balls, and that also is going to affect how they work in the body. It's going to change what they want to attach to. It's going to want to attach to something that's electron poor, for instance. Another example of the way that humans use chemistry is to make recreational drugs, for instance. Now, actually, methamphetamine does have a medicinal use, and so does the other molecule here. But just look how simple methamphetamine's structure is. And it has a very interesting bond here that we're going to talk about later on. But I'll tell you now, it means it's racemic. So we probably won't talk about that again until later on. But it's got a very interesting bond there. But otherwise, the structure is relatively simple. And then over here on the right-hand side, we have lysergic acid diethylamide. That's LSD. And again, look how complex that structure is. But that structure too basically goes into your bloodstream, gets into your brain, interacts with certain parts of your brain, and causes hallucinations, right? So both these molecules, just like the aspirin, are going into the bloodstream, interacting with some protein in the body that basically senses the chemical nature of the blood and then changes it in some way, or else reports in your brain with the LSD that is firing neurons randomly, and you are interpreting that as an experience. So all that's happening there is the LSD molecules are pairing with neurons and making them fire. And that, again, that comes from its structure. Notice how electron rich it is up at the top. We've got nitrogens with lone pairs, oxygens with lone pairs, and then there's quite a lot of this drug in the middle that doesn't have very many electrons at all. Lovely. So that takes me to the end of this lecture. Hopefully that made some sense, and I look forward to seeing you in the next one where we're going to dig down a little bit deeper into these shapes. Thanks very much.